In this lesson, we're going to be looking at derivatives of polynomials and the derivative of the natural log function. Let's start out by looking at a horizontal line. What is the derivative of a constant function? If we wrote the equation of this line, it would be f of x equals 2. That would be this function. So if I wanted to find, let's say, the derivative of the function when x equals 2, I would be looking for f prime of 2. Let's draw in the tangent line. And it appears that the tangent line has a slope of 0. If I wanted to find the slope of the tangent line when x equals 6, if I draw in the tangent line there, we can see again the slope of the tangent line is 0. That indicates that if we take the derivative of any constant function, so y equals f of x is a constant function, if we take the derivative of that function, that will equal 0. So the rate of change of a constant function would be delta y over delta x. And if we looked at this through the limit process, we can see in the numerator we'd get c minus c as h approaches 0. So we have 0 in the numerator, and h is approaching 0, but any number, 0 divided by any number is going to equal 0. Let's look at the function y equals x and do the same analysis. If we wanted to find the slope of the tangent line at any particular point, let's say we wanted to find the slope of the tangent line when x equals 2. So we draw in the slope of our tangent line, and we could calculate the slope of that line. If we wanted to find the slope of the tangent line when x equals -4, we would draw in our tangent line and find the slope of that tangent line. Now hopefully we notice that the slope of the tangent line is the same as the slope of that function. So the slope of y equals x, if we put it into the form y equals mx plus b, we know b is 0 in this case, but the slope of the line is 1. So we should be able to make a conclusion about the derivative of our function x. So if we wanted to find the derivative of this function, f of x equals x, we would have f prime of x, we saw, would equal 1, because the slope of this tangent line, wherever we choose the value of x, is going to be the same as the slope of this line, and we said the slope of the line is always 1. So f prime of x equals 1. We could go through the limit process and show this is true using limits also. Now this notation we talked about earlier, this means the derivative of x, and x is our function. So these are saying the same thing. So we found that the derivative of the function x equals 1. Let's take a look at the derivative of x squared. So I went through and used the limit process, and we know how to do this. We take the limit of f of x plus h minus f of x divided by h. So just kind of look at that, make sure you understand where that, let me just write our general slope of a tangent line up here. We would have f prime of x equals f of x plus h minus f of x divided by h. And we would take the limit as h goes to 0. So that's what we are doing right here. So we found, using the limit, that the derivative of x squared equals 2x. Let's be looking at patterns here. Next, we're going to look at the derivative of x cubed. So if our function is x cubed, and if we're trying to find the derivative, we would use the limit again. And we find that the derivative is 3x squared. The derivative of x to the fourth, we can use the limiting process, and we would get 4x cubed. So look at what we're trying to find the derivative of. First it was x, then x squared. Here we found the derivative of x, x squared, x cubed, x to the fourth. So for x squared, here's our derivative, 2x. For x cubed, here's our derivative. For x to the fourth, here's our derivative. So we're looking for a pattern. So it appears that we have a pattern here, and if you see the pattern, you should be able to just tell me, what is the derivative of x to the fifth? The pattern appears to be we pull the exponent down in front of our x and then subtract 1 from the exponent. So the derivative for x to the fifth would be 5x to the fourth. So the derivative for x to the sixth, we bring the exponent down in front and then subtract 1 from the exponent. So it would be 6x to the fifth. So at this point, we may be able to generalize if we have anything in the form of x raised to the n power, we should be able to find the derivative by pulling the exponent down in front and then subtracting 1 from the exponent. And this is true. That's how we can find the derivative of any expression or any function in the form of x to the n. So you can see, looking for patterns here, this will greatly simplify finding derivatives. We're looking for these patterns so we don't have to go through this limit process any longer. Now, if we looked at the proof of why this works, we would go back to the function f of x equals x to the n. So we're trying to show what the derivative of x to the n power is. So through our limit process, we're going to try to show this. So we have the limit of f of x plus h minus f of x divided by h as h goes to 0, which gives us then this. Now, before we proceed with this, if I have x plus h to the, let's say, the fifth power, there's a process that we can use to greatly simplify finding or expanding this binomial. So that process involves, one way to do it is Pascal's triangle. Do you see, to create Pascal's triangle, I always have a 1 on the outside, and then I'm just adding these two numbers. Add these two numbers to get this one. Add these two numbers. I'm going to do it one more time because I have x plus h to the fifth. So I'm looking for the fifth row, where the first row here is 0. This is the first row, second row, third row, fourth row, and fifth row. So when I add these, I get 5. Add these 10. Add these 10. Add these 5. And always 1 on the outsides. Now here's the pattern. These give me the coefficients for each one of the terms of x plus h to the fifth expanded and then collecting all of our like terms together. So if I showed you the pattern here, the first term we know would be x to the fifth, but it would have a coefficient of 1. So it'd be 1 x to the fifth. And actually we could say it's h to the 0 because that's just 1. Now, this is going to be my next coefficient, 5. So it would be plus 5. Now I subtract 1 from this exponent, but then add 1 to this exponent. My next coefficient would be coming from here, 10. I subtract 1 from the exponent, add 1 here. Those always have to add up to be 5. My next coefficient is 10, so I'd have x squared h to the first. My next coefficient is 5, so I'd have x h to the fourth, plus the last coefficient would be 1. Now this would be x to the 0, h to the fifth. So that's what we would get if we take x plus h to the fifth and expanded it and then collected all of our like terms. You can see this process very much simplifies expanding a binomial. Now, if you notice, this is what's important to our proof above, is that these can also, we can find these another way. Like I said, this is always going to be 1. The next one, if I called the power here the fifth, that's our n. Whatever that is, we're calling n. So we're going to be able to raise the binomial x plus h to the n power. So this one, in this case, n would be 5, but I'm just going to write it as n now so we can see the pattern. Here, this 10 would be n times n minus 1 divided by 2 factorial. This would be n times n minus 1 times n minus 2 over 3 factorial. The next one would be n times n minus 1, pen's not working down here, times n minus 2 times n minus 3 divided by 4 factorial. Now, in this case we said n is 5. So do you see this would be 5 because n is 5. Here we'd have 5 times 4 divided by 2, which is 10. This one would be 5 times 4 times 3, all divided by 3 factorial is 3 times 2. Here we get 20 divided by 2 is 10. And this one that we can barely see would be 5 times 4 times 3 times 2, all over 4 factorial, which is 4 times 3 times 2 times 1. So after we reduce, we can see we're left with 5. which gives us this one. So you can see that's another way to find our coefficients, and that's the technique we're going to use for this proof. So let's get a little bit more room here, and then let's continue on with our proof. We're going to show that what the derivative of x to the n equals. Need a bigger eraser. All right. So let's see if we can fit our proof in here now. And if we need to erase the rest of it, we can. So let's go back up to here now and rewrite this. This would be the limit as h approaches 0. Now, when we expanded this out, we know we would get 1 times x to the n, h to the 0. I'm not going to write the h to the 0. Plus, now we would have n, because that is the exponent, times x to the n minus 1, h to the first power, divided by, we could say 1 factorial, which is just 1. Plus, then we would have n times n minus 1, all divided by 2 factorial, x to the n minus 2 h squared. Now the last term would simply be our h to the n power. That would find this x plus h raised to the n power. But then we have minus x to the n, and then we're dividing that by h. Now if we try direct substitution, you can see we have x to the n. All of these have h's in them, and then minus x to the n, we would get 0 over 0. So we can see these cancel each other. All the other terms have an h in it. So you probably are thinking, well, let's factor out an h then. So let's factor out that h. So if I factor out the h from here, we're left with n times x to the n minus 1. Now in this term here, we would have plus n times n minus 1 all over 2 factorial x to the n minus 2 times h, plus all of these terms in between. And when we factored out an h from here, we'd have h to the n minus 1 h's, and this is all divided by h as h goes to 0. Now we can see the h's reduce. Notice that each term in what's left, except the first term, has an h. This has an h in it. That would go to 0. All of these terms in between have h's. Those would go to 0. This goes to 0. So what do we have left? Well, we have this. It doesn't have any h in it. So we would just have n times x to the n minus 1. And there we have found our derivative, f prime of x. And that's the proof for finding the derivative in the form of any function in the form of x to the n power. And let me erase all the ink on the slide so you can see that. Use the power rule to find the following derivatives. So for this one, the derivative of x to the 7th, we'd pull the 7 down in front, subtract 1 from the exponent. 7x to the 6th. Y equals t to the 9th. Pull the exponent down in front, subtract 1 from the exponent. So the derivative is 9t to the 8th. Now, what if we have a function like 1 over x? That is not in the form of x to the n power, but can we rewrite 1 over x in the form of x to the n power? That's the key to many of these derivatives. We rewrite it so it is in the form of x to the n. We cannot just say that the derivative, well, that would just be, if this is x to the 1 here, we can take the 1 down in front, subtract 1 from the exponent. We cannot do that if this is in the denominator. It has to be in the numerator. So we can rewrite this so it is in the numerator. Our variable is in the numerator. And if we rewrite this, we can rewrite it as x to the negative 1. So now we can apply the power rule. Now we would finish this off by rewriting it as negative 1 all over x squared. We want positive exponents in our final answer. How would we rewrite this in order to use the power rule? Well, we know the square root of x can be rewritten as x to the 1/2. Therefore, bring down the power in front, 1/2, and subtract 1 from 1/2, and we get x to the negative 1/2. And then we rewrite it with a positive exponent and then change it back into square root form. Here's another one. We can rewrite this as x to the 2/3 and then use the power rule. So bring the 2/3 down in front, subtract 1 from the exponent, and again we would rewrite this one with a positive exponent, so it would end up being 2 divided by 3x to the 1/3, which is 2 all over 3 times the cubed root of x. Here we can rewrite as x to the negative 2 power. So bring the negative 2 down in front, subtract 1. Negative 2 minus 1 is negative 3, and then rewrite it with a positive exponent. Find an equation of the tangent line to the curve of x times the square root of x at the point 1, 1. Let's see if we can use our power rule. I can rewrite x, the square root of x, as x to the 1/2. I have like bases, so I can add the exponents. So this is the same as, because this is just 1 over 1. If I get common denominators so I can add them together, that's 2 over 2 plus 1 over 2 is 3 over 2. Now I can find the derivative, so I can find the slope of the tangent line. Bring down my power, and then I'm going to subtract 1. I just get a common denominator. So there's the derivative of the function. Now I want to know the slope of the tangent line when x equals 1. So we're looking for y prime of 1. So if we plugged 1 in for x, we'd get 3/2 times 1 to the 1/2. We know the square root of 1 is 1, so we would get 3/2. So the equation of the tangent line, we have so far that the slope of the tangent line when x equals 1 is 3/2. And we need to find our b, so we can plug in 1 for y using this point, and 1 in for x, and now we can solve for b. So b equals 1 minus 3/2. So b equals -1/2. So the equation of our tangent line is y equals 3/2 x minus 1/2. And I'm just going to leave it in slope-intercept form. Here's the graph of x times the square root of x, the red graph, and then I just graphed y equals 3/2 x minus 1/2, and you can see its tangent when x equals 1. Now we're going to look at how we can find new derivatives from old. The constant multiple rule. If we have something like 3x to the 4th, and we're trying to find the derivative, that's what this means here, find the derivative of 3x to the 4th. I could rewrite this as 3 times the derivative of x to the 4th. Now we know the derivative of x to the 4th would be 4x to the 3rd. And we would just multiply that times 3, which would give us 12x to the 3rd. If you notice, we could do that whole process in one step. When we bring down that 4, we know we're going to multiply the 3 times the 4 and then subtract 1 from the exponent. So we can do that all in one step. But this is called the constant multiple rule. Find the derivatives of the following functions. So we have y equals 3x to the 6th. So if we're looking for the derivative, let's use the constant multiple rule. We know we can bring that 6 down in front and multiply it by 3 and then subtract 1 from the exponent. So we would get 18x to the 5th. Here, the derivative of our function, we have a -1/3. We're going to bring down the 3 and then subtract 1 from the exponent. You can see we would get -3 over 3 is -1, so we'd have -x squared. F prime of t. Now, we don't write the power of 1, but it is there. If we bring the 1 down in front, we'd have -1t. Now, if we subtract 1 from 1, we get 0. So we end up with -1 because t to the 0 is 1. The sum rule. If f and g are both differentiable, then these are equivalent. This is indicating if I want to take the derivative of 3x to the 5th plus 2x to the 7th, I could take the derivative of them separately and then add them together. Now, typically in practice we don't do this, but we are using this sum rule when we do it all at once. This would be 15x to the 4th plus this would be 14x to the 6th. However, if we just did it all at the same time, we would get our 15x to the 4th plus 14x to the 6th. So we can take the derivative term by term and then add them back together. The difference rule, same idea as the sum rule, only we're subtracting. We can take the derivative term by term and then subtract them. So an example, here we have a polynomial with 5 terms. We could go through and take the derivative of each term separately and then either add or subtract them back together. But as I said, typically what we'll do is we will just look at this and say, we understand we can take the derivative of each separately and then add them or subtract them. So we would just say, well, this is 5x to the 4th minus 12x squared plus 18x minus 2. The derivative of a constant is 0, so that goes away. Find the points on the curve of x to the 4th minus 6x squared plus 4 where the tangent line is horizontal. Now, give this a little bit of thought before you continue on. How would I find where the tangent lines to this curve are 0? And I'm just going to put in general right now. Let's say I have a function that looks like this. It's asking me, where are the tangent lines to this curve? What values of x would it equal 0? So I can see right here the tangent line would be 0. Here it looks like the tangent line would be 0. So the idea is, how can I find these x values where the tangent line is horizontal, which means the slope of those tangent lines are 0? So if you formulated your plan, you probably thought, I need to find the derivative of my function. So y prime would be 4x cubed minus 12x. Now, when we take the derivative of 4, that goes to 0. And then we want to know, this represents the slope of the tangent lines. We want to know where that equals 0. So we will set the derivative equal to 0. And then we can solve this equation. So if we factor out a 4x, we'd have x squared minus 3. We would set each factor equal to 0. Here we would get x equals 0. And when we solve this one, we would get x equals plus or minus, because when we take the square root of both sides, we have to take the positive and negative value. So we would get x equals plus or minus the square root of 3. Now, what does that represent? What did we just find here and here? We found where the slope of the tangent line to the graph of x to the 4th minus 6x squared plus 4 equals 0. Or another way of saying that is where the tangent lines are horizontal. So let's take a look at the graph of our function x to the fourth minus 6x squared plus 4. There's the graph. Now we said that we would have horizontal tangent lines at plus and minus square root of 3 and at x equals 0. And you can see those. There's your tangent line at 0, and here are your tangent lines at negative square root of 3 and positive square root of 3. And in calculus, those are going to be some important points when we start solving some problems later on in calculus. So very often we use this technique to find where the slope of the tangent line equals 0. Exponential functions. We are going to take a look at the derivative of e to the x. It's called the natural log function. Now, if we're going to try to find the derivative of e to the x, we're going to go back to our limits and see if we can make a determination of what the limit would be as h approaches 0, because we know this is the definition of a derivative. So let's see if we can determine what's going on here. So if we plug in x plus h everywhere we see an x in our function, we'd have e to the x plus h minus e to the x divided by h. This can be rewritten as e to the x times e to the h. Now, as h goes to 0, notice this doesn't have an h in it, so we could say it's a constant. And we notice we have an e to the x there and here, so we could factor that out. So we'd have e to the x times e to the h minus 1 all over h as h goes to 0. Now we said e to the x is considered a constant, so I'm going to bring that constant out front. So we need to be able to determine what does this limit of e to the h minus 1 over h as h goes to 0 equals. Now you could do that with your calculator, and that probably wouldn't be a bad idea. Just go ahead and verify. You would plug in e to the x minus 1 divided by x, and then look what happens as x approaches 0. See what value you get. I'm going to do this algebraically. Now, what we need to know is that the definition of the letter e as a limit can be written as the limit, as h goes to 0, of 1 plus h raised to the 1 over h power. If you looked at that limit on the right side, and again, on your calculator, just replace the h's with x, 1 plus x raised to the 1 over x, and look at what happens as x goes to 0, you would see you're approaching 2.71, which is the value of e. Now, for small values of h, e would be approximated by 1 plus h raised to the 1 over h power. For small values of h, e would be approximated by this. So if I looked at raising each side to the h power, we would have e to the h equals 1 plus h. Because when we would multiply these two exponents together, we'd get h over h is just 1. Now we can use this to complete what we are doing down here. So let's replace See, we have e to the h defined as 1 plus h, so we're going to replace that here. So we would have e to the x times the limit as x approaches 0. Now, e to the h we're going to replace with 1 plus h. That replaces our e to the h. And we still have minus 1 all over h. So we would have e to the x. Now here the ones cancel, and we can see h divided by h is just 1. So we'd have the limit of 1 as h goes to 0. And we know the limit of 1 as h goes to 0 is just 1. So we get e to the x. So what did we just find? We were looking for the derivative of this function e to the x, and what did we get? We have e to the x. So in conclusion, if we have a function e to the x, we just found that the derivative of e to the x is e to the x. Let's use this to find the derivative of this function. We have our function is e to the x minus x, and we are looking for f prime of x. We just found that the derivative of e to the x is e to the x, and we know the derivative of x to the first power. We would bring down the 1, subtract 1. So we would have e to the x minus x to the 0 is just 1. We'd have e to the x minus 1. There's our derivative. There is our function e to the x minus x and e to the x minus 1. That's our derivative, and there's our original function. At what point on the curve of e to the x is the tangent line parallel to the line y equals 2x? This problem, we have the function, it says e to the x. It's asking us what tangent line, at what value of x would the tangent line to this curve be parallel to the line y equals 2x. So if I say, I missed the origin, but that should be going through the origin. If this is y equals 2x, if I chose the value of x here, we can see that tangent line would not be parallel to y equals 2x. We can see it someplace in here. This tangent line would be parallel to the line y equals 2x. So we are looking for this x value. We need to find that value of x so that the tangent line to e to the x is parallel to 2x. Now, give this problem some thought before you continue. See if you can solve this problem. We want the slope of the tangent line, so we need to find the derivative of our function. Well, derivative of e to the x is e to the x. That gives us the slope of our tangent lines. Well, the slope of the line y equals 2x, the slope of that line we know is 2. And we want the slope of our tangent line to be 2, so we're going to set e to the x equal to 2. Now if we solve by taking the natural log of both sides, this side when we take the natural log of e to the x, that just equals x. So we get ln of 2. So what does this represent? That would be the value of x, where the slope of the tangent line to the curve of e to the x is parallel to the line y equals 2x.